Resume. Okay, so let's continue. Okay, so before the break, we discussed nonlinear function approximations, right? Like, so now to summarize the class of function approximation, like our algorithms that we have seen so far in terms of function approximation. So we have seen tabular methods, right? And after that, we saw linear function approximators. Then we saw nonlinear function approximators, right? Now, in terms of how to integrate these function approximators with reinforcement learning algorithms, like so for on-policy algorithms, it is really simple. So whatever we did last week, you can just take the linear function approximator that you used there and switch it with the neural network. Okay, most probably it will work, but sometimes it won't, I guess. Just give me a second. Yeah. So we will talk about it. So we'll talk about the issue of nonlinear function approximation in general. But the general idea is like with on-policy, we have seen how to do this with on-policy methods. Okay. Now for the rest of today, like we're going to talk about off-policy methods. Okay, with function approximation. Okay. Now, in terms of extending a tabular off-policy method to something with function approximation, the extension is trivial. Okay, so all you have to do is go take the update function. Instead of updating the row in the table, you're going to update the weights of the parameter. It could be a linear model or it could be a nonlinear neural network. Okay. However, off-policy function approximation methods don't converge as robustly as on-policy methods. Okay, like at least for the next 20-30 minutes, we are going to discuss why that is the case. But before that, a very quick recap of off-policy learning, given that it has been 2 to 3 weeks, you have seen this. So a quick recap of off-policy learning. Now, maybe before that, can someone tell me what is the difference between on-policy learning and off-policy learning?
In off-policy, we have two policies, like target policy and behavior policy.
Okay.
We are going to use behavior policy to learn the target policy.
Okay. So what about on-policy?
During the learning, we are going to learn the policy.
Okay. Can someone else give me an example for on-policy algorithm and off-policy algorithm? Who said Sarsa? With mask on, I really cannot know who says Sarsa. Who said Sarsa? I heard Sarsa.
I said Sarsa is on policy.
Okay, yeah, that's good. So Sarsa is on policy. Okay, that is good. Off policy algorithm?
Q-learning.
Good. So Sarsa is an example for on policy algorithm, and Q-learning is an example for off policy algorithm, right? So now I will repeat what she mentioned, like about what is off policy learning. So the goal of off policy learning is to learn a value function, okay, for a target policy phi, okay, given data due to a different behavior policy. Is that clear? So you have a separate target policy that you want to learn about, but you're learning using a behavior policy B. Okay. Now, why would someone do that? There are many reasons, right? Like, so for example, if you want to learn greedy policy, okay? So we saw that there is a problem in doing that if you are also using that for the behavior, right? And so you want to be more exploratory, like when you're learning. So it's easier if you decouple the behavior policy and target policy, so that like you're learning about a policy which is different from what you are behaving. That's why it's called off policy, right? So now, in the case of prediction, right? So both pi and b are static and given. So when you are doing value function prediction, then somebody gives you the behavior policy and target policy and just ask you to estimate the value of the target policy, right? So given a fixed b, can you learn the value for a fixed pi, right? However, when you are in the control setting, things are complicated. So we are learning action values, right? However, both pi and b are changing. Like if you take Q learning as an example, right? So pi in Q learning is basically greedy policy with respect to Q, right? And can someone tell me what is the behavior policy in Q learning? Can we get some answers from Zoom as well? People in Zoom, like for these simple questions, all of you can answer. Any answers? So what is the behavior policy in Q learning? Aren't you implementing Q learning for your assignment? So what is it? Epsilon greedy, right? Like, so your behavior policies, it has to be some soft epsilon soft policy, but we normally use epsilon greedy, which is more exploratory when compared to pi, right? Now this is off policy learning, like a quick recap of off policy learning. Now, what are the challenges in doing off policy learning with function approximation? Okay. Now, in general, there are two challenges in off policy learning. Okay, so the first challenge is the issue of the target of the update. Okay, now when you update your value function, the target that you have is estimated with respect to the behavior policy. Now I want to do some correction to this update so that it is estimated with respect, it is as if it is estimated with respect to the target policy. Now, I think we have already solved this issue. So how did we fix this issue? Importance sampling, right? Like, so we did importance sampling, which is basically the idea of considering the relative probability of this action in both the cases and doing correction to my update, right? So now this issue arises both in tabular and function approximation, okay? Even when you do function approximation, you have to consider this importance sampling, like if you want to correct this issue, okay? Now, there is an additional issue, a new issue that arises only in off policy function approximation case, okay? So this is the issue of distribution of updates. Okay, so this is only in function approximation. Okay, now if you think about how off policy learning works, the way in which you are updating, the distribution of updates to the states is based on the behavior policy, not on the target policy, right? Like, because behavior policy is what you are acting out in the environment. So you get some states, you observe some states, you make updates to the states. Now the distribution of updates follows the distribution of the behavior policy, right? Now, this was kind of fine in tabular setting because we know that tabular setting is one of the nice setting where like you just do things for long enough, you're going to converge, right? Now this is not the case with function approximation. Now, if you remember our discussion last lecture, so I told you that linear function approximation converges as long as you follow the distribution of what you are estimating, okay? Or in other words, if you stay on policy in your distribution of updates, then these methods would converge, okay? But this is a problem for off-policy learning, because in off-policy learning, like, we don't do the updates based on on-policy distribution, right? So now, in this case, we have some issues. Like, the issue is your updates are not going to be stable, okay? Stability of function approximation is guaranteed only if you do on-policy updates, okay? So in the case of off-policy upgrades, all the gradient and semi-gradient methods that we have seen, like, they are not going to be, well, at least we cannot prove yet that they are going to converge. And in fact, we have examples, counter examples, which shows that these algorithms would actually diverge. Okay, so we will see several counter examples today. But before that, let us first extend the existing off-policy algorithms to function approximation. Any questions so far? Okay, so now we're going to talk about semi-gradient methods, but extended to off-policy setting. Okay, now, so to convert tabular off-policy methods to semi-gradient form, all we have to do is, like, very simple, like, just replace your tabular updates or row updates to updates to the weight vectors of some function approximator. Okay. However, we need important sampling to correct our issue, like mistakes here. So we will be using per step important sampling ratio. Okay. So which is basically, let's say, rho t, which is rho t to t. If you can remember what we did with important sampling and off-policy learning in the Monte Carlo lecture, so we constructed rho for a subsequence, right? Like 1 to t. So that's why I'm putting rho t to t. Okay, so this is per step important sampling, which is given by the probability of this action with respect to the target policy divided by the probability of this action with respect to the behavior policy. Okay, now we are going to do one-step methods. So that's why I'm constructing the one-step important sampling. Okay, and of course, it is very easy to extend this to n-step method. Like, you just need to do rho t to t plus n, right? So first, let's do one-step methods. So I can directly write the equations now. Like, so we have seen these things many times. Like, so for example, let's talk about semi-gradient off-policy TD. Okay, and I'm going to do a one-step state value algorithm. Okay. Now the update for this algorithm is going to look something like this. So WT plus 1 is equal to WT plus alpha times the target, right? So now if you remember, for on-policy methods, so we had some del t and then the gradient, right? Where del t is given by the target. So RT plus 1 plus gamma times V of ST plus 1 given WT minus V of ST given WT. Right? So this is your TD error. So this is your current estimate for this particular state. You want that to be as close as possible to reward plus gamma times the value of the next state, right? Now, if you do a squared error, like squared error for your value function loss, then when you differentiate, the square goes away. So that is why you have just del t here, and then you differentiate the value function, right? So can someone tell me why we call this as a semi-gradient method instead of gradient method?
Because you're not taking the gamma v to account when you are taking the gradient.
Yeah, so because when I'm computing the gradient here, I'm computing the gradient only with respect to this part. However, my target is also a function of WT, right? So if we take gradient with respect to that, then there is going to be some issues. So to avoid that, like we just take gradient with respect to the one part, treating the target as a constant. Okay. So now this is not off policy TD. This is on policy TD. Now, how do I make this an off policy TD? I just need to do correction, right? So now I will add a row T here. Is that clear? So now I can add a row T here and behave with the behavior policy and learn the optimal policy or the target policy. Is that clear? So extensions are trivial, okay? So the question is this algorithm going to work? Is this algorithm going to be stable and converge to a good state, right? Like, so that is what we are going to discuss. But before that, let's extend some more algorithms. So next I'm going to extend semi-gradient expected SARSA. Okay, now this is a one-step but action value algorithm. Okay, now in semi-gradients expected SARSA, WT plus 1 is going to be WT plus alpha times del T Q of ST AT given WT. Okay, where del T is given by RT plus 1 plus gamma times. So this is like Q learning but expected Q value, right? So it's between Q learning and SARSA. So you have an expectation. So summation over all possible action, phi of A given ST plus 1, Q hat of ST plus 1, A given WT. This is the whole target. So minus Q of STAT given WT. Right? Now, it so happens that for semi-gradient expected SARSA, you don't need to do the importance sampling. Okay, it's, well, at least for one step case. So it's because we are considering action values here. So when you're thinking about one action, you don't need to consider other actions while estimating the value of this action. Okay, so this is simpler case where you don't need importance sampling. However, once you move to the n step case, you should have importance sampling for both n step TD of policy TD and n step semi-gradient expected SARSA. Okay, so let us actually write just the n step semi-gradient expected SARSA. Okay, now it's going to be very similar to SARSA except for the fact that I'm going to consider n step returns. So WT plus n is going to be WT plus n minus 1 plus alpha times. Okay, now I need important sampling, but the important sampling is from T plus 1 to T plus n minus 1. So rho T plus 1, rho T plus 2 to rho T plus n minus 1. Then inside you have GT to T plus n minus Q hat of STAT given WT. Then the gradient with respect to Q hat of STAT given WT. Sorry, this is WT plus n minus 1. Okay, where GT to T plus n is the truncated n step return. Now, can someone tell me how to write GT to T plus 1? Someone who has not answered so far. So what would the truncated n step return look like? Okay, I'm just curious. How many of you know this? Raise your hand. Okay, so not a lot of you. So we want to compute the return but truncated at n step. So how would you do that? So it's going to be RT plus 1 plus gamma times RT plus 2, right? plus gamma of n minus 1 times RT plus n. So after that, you truncate the rest. So plus gamma n of q hat of st plus n, at plus n, given w t plus n minus 1. Right? Okay. People who did not know this, you should go and revise your in-step learning. Okay. So far what I have done is really I took every possible off-policy learning algorithm and I just converted it into the function approximation case, like by just computing the gradients, right? So now, are these algorithms going to converge all the time? So simple answer is no. Like we are going to see several examples for why they would not converge before we start discussing the high level picture, okay? Now we are going to look at some examples for off-policy divergence. Now this divergence happens mainly because of the second issue, which is the distribution of updates, okay? So let's start with some simple example and then see more complex example. Like the first simple example is, consider I have a very large MDP, okay? Now, we are going to consider just two states in this MDP, okay? So let's say I have some state 1, and from state 1, there's only one possible action, and this possible action takes you to state 2. Is that clear? With a reward of 0. Okay. Now, I'm using function approximation, right? So now let us say that my function approximation is a very simple function approximation. There's only one W, like W is a scalar. Okay. Now, state 1 is represented by W, state 2 is represented by 2W. So how could this happen? Because let's say my function approximation is just W. Anything you give, it's multiplied by W, okay? Now, x of S1 could be 1 and x of S2 could be 2. So you feed the first state, my function approximation will tell the value is W, 1 times W. You feed the second state, my function approximation is going to tell you like 2 times W, which is 2W. Is that clear? Is the setup clear? Now, let us assume that initially W is equal to 10. Okay. Now, can someone tell me the value of the first state given W? What is the value of the first state? This doesn't require any revision. So it's 1 multiplied by W, right? Like, so it's 10. What is the value of the second state? 20, right? So now I'm doing, let's say, one-step TD. Okay, so I want to update the estimate. Like my behavior policy here is, well, in this case, like it doesn't matter what is the behavior policy because there's only one action possible, right? So from W there's only one action and it takes you to 2W. So now when I take an action from state 1, I want to update the value of the state, right? So value of my current state is 10. There is 0 reward. Okay. Now let's say gamma is almost close to 1. And can someone tell me what would be the TD error for the first state? What would be the TD error for the first state? So my gamma is very close to 1. You can just assume that it is 1, just for making it things simpler. Okay. So now my first state's value estimation is 10. From a state of value estimation 10, I go to a state of value estimation 20. So what is the TD error?
Minus 20.
What?
So plus 20.
It's not plus 20.
10.
10. It's just 10, right? The difference between this, you want the first state to be reward plus gamma times the value of the next state. So it's 0 plus 1 times the value of the next state. So the TD error in this case is going to be close to 10, right? Now let's say my learning rate alpha is equal to 0.1. then how would you increase the value of W? So now W is going to be increased by 10%, 10% of 10. So it's going to be increased by 1. So my new W is going to be 11. Okay. Now with this new W11, what is the value of the first stage? It's 11. What is the value of the second stage? It's 22. I took a step to reduce my error, right? Now what is the new TD error? 11. My TD error is increasing. So my TD error now is 11, close to 11, which means what, like I need to take 10% of 11. So what would be my new W? Now my new W is going to be 12.1, right? So now the error is even increasing. Like it's not increasing just by 1, it is increasing by 1.1. Now as you can see, this is going to exponentially, like this will reach infinity very fast. Okay, so like it keeps increasing and there is no way to stop this, like, and this is going to diverge to infinity. Is that clear? Yeah.
Yeah, but this more looks like an issue with representation and not issue with like off policy or on policy thing, right?
That's a very deep observation. So we are going to talk about it like in the third half probably. So yes, this is an issue. Okay, maybe I'll tell it right now. So this is the issue because of 3 things here. Okay, so this is the issue that happens because you are doing off policy. Well, maybe I will not give it all away. So I'll just accept what you said. This issue happens because of the off policy learning combined with the function approximator. For now, right? Like so, and there is also a third component here which we haven't discussed much, which is the idea of bootstrapping. Like you're bootstrapping here, right? So there are 3 things which combines together to this, like form this issue. Okay, so this issue happens because you are doing bootstrapping. You're learning one state's value from another state, because you're using off-policy learning, and because you're using function approximation. Okay, so we're going to discuss. So we're going to call this 3 components a deadly triad. Like so. Well, like probably in like 20-30 minutes we'll go there and we will discuss that if you can remove one of these 3 components, then you are safe. But when you combine all these 3 components, then you are not going to have a stable system. Okay, we're going to talk about it in detail later. Okay, so for now let's continue with this story. So now we can actually characterize when the system will become unstable. Okay, to do that, let's just compute the TD error. The TD error del T is given by RT plus 1 plus gamma times value of ST plus 1 given WT minus value of STWT, right? So in this case, this is basically 0 plus gamma times value of the next state is given by 2WT minus the value of the current state, which is WT, right? So this is basically 2 gamma minus 1 times WT. Is that right? Now, an off policy semi-gradient TD update is given by WT plus 1 is equal to WT plus alpha times rho T times the gradient, right? Okay, I think there is a typo, like there's a mistake in the notes. It has to be del T, then the gradient with respect to V. Okay, now this is basically WT plus alpha. There's only one action possible, so rho in this case is going to be 1. Okay, and 2 gamma minus 1 times WT, right? And when you differentiate the function approximation with respect to W, you'll get 1. So this is basically 1 plus alpha times 2 gamma minus 1 times WT. Okay, so it so happens that at every time step, you are multiplying or you're scaling your WT by this term, 1 plus alpha times 2 gamma minus 1. Now, if this alpha times 2 gamma minus 1 is greater than 1, right? Sorry, the whole term, like if it is greater than 0, right, then the system is going to be unstable. Like so, if 1 plus alpha 2 gamma minus 1 is greater than 1, okay, then the system is unstable. So when would this happen? For what value of gamma? So this will happen when gamma is greater than 0.5. Okay, so if you have a gamma which is greater than 0.5, then this system is going to diverge. So remember, like, note that the stability of the system is not decided by alpha. Alpha only speeds up or reduces the rate of divergence, but divergence will happen irrespective of however small your alpha is. Okay, so which is interesting. Like so, learning rate is not causing this instability. It is actually a fundamental, much more fundamental problem than the learning rate. Okay, so often we need to be very careful with the learning rate for divergence, but even with a very carefully chosen learning rate, you're going to diverge. And it's because of this fundamental problem, which is a combination of these three things. Is that clear? Yeah?
Yes, I was saying like off policy is not really playing any role, right? So your rho is 1.
That's a good question. So now, where is the role of off-policy learning here, right? Now remember that if you're doing on-policy learning, okay, now let's go here. If you do on-policy learning, now after visiting state 2, you will visit another state from state 3, like state 2, like right, like so. So basically, you will be updating your W based on other transitions which are following. Okay. Now, if the other transition tells you that the return is small, then you will be reducing the value. Okay. Now this happens always in on-policy learning, but in off-policy learning, it could happen or it could not happen. Okay. It really depends on how good is your behavior policy. If your behavior policy is going to give, let's say, 0 probability for that particular action that the target policy would take. Okay, now that should not happen. But if your behavior, so the issue is like if your behavior policy is giving very low probability or close to 0 probability for some action, if it gives 0 probability, then the transition is ignored, right? So now the moment you introduce behavior policy and off policy correction, it could very well be the case that you will not update state 2 at all. Like you will just keep updating state 1. Now, there is a chance for this to happen in off policy, but not in on policy. Okay. Now, in on policy learning, like each time there is a transition from S1 to S2, there should also be a transition from S2 out to somewhere. Okay. And rho T is not going to be 1 in that case. Okay. So that transition is going to reduce the W. So this is not happening in off policy. Is that clear? Okay, so far we have seen a really tiny example, right? Like, so this is 2 states in a part of an MDP. So how severe is this problem? Like, is this going to happen in every problem that we are going to see? Like, or is this going to happen for a complete, can we come up with a complete MDP where we show that this MDP, off policy approximation will always diverge, okay? So there is another example, like, so this is a counter example given by Bad. So Bad's counter example. Okay. Now, this is a complete MDP. So I'm not sure where I have that. Okay, it's here. It's going to be confusing with the nodes, so I'll just cut this. Put it here. Okay, this is bad. Okay. So here you have a 7-state MDP. Okay. So there are two possible actions, solid action and a dashed action. So whenever you take a solid action from any state, you always go to state 7. Is that clear? Whenever you take a dashed action from any state, with equal probability, you go to one of these 6 states. Okay. Now the reward is going to be 0 for all on all transitions. So reward is 0 on all transitions, and gamma is 0.99. Is that clear? Now, yeah.
What happens when you take the dashed action?
When you take a dashed action, like with equal probability, you go to all the 6 states, any of the 6 states. So it's a stochastic action. It takes you to one of the 6 states. Okay, now reward is 0 for all the transitions. So what would be the true value for all these states? 0, right? So all the, like if I do the estimation, I should get 0 for all these states. Okay. Now we are going to consider a function approximator. Well, W is given by 8-feature representation. Okay. So for example, you can see the representation in every state. Like so, for example, state 1 is represented as 2W1 plus W8. Okay. It just means that x of 1 is given by 2, 0, 0, 0, 0, 0, 0, 1. So I have a 8-dimensional input representation. Like this has been carefully constructed to show the divergence. Now you see that like each state has some feature representation. So one thing to note here is like the feature vectors is a linearly independent set. Okay, which means it should be easier to do function approximation like without any issues. Now the value of the state should be equal to 0 for all states, yes, which means the optimal W in this case is equal to 0, right? I'm looking for, I'm checking if, I'm going to check if I converge to W is equal to 0. Is that clear? Okay. Now, for this particular example, right, you can implement it. It is actually very simple. You will see that semi-gradient of policy TD is going to diverge for any possible configuration that you can think of. Okay, so all the estimates are diverging. Now, is this could be because of several reasons, right? Like so with TD learning, there is stochasticity, there is asynchronous nature of updates, right? So now we need to identify what is causing this issue. So to do that, we will also run a semi-gradient version of dynamic programming. Okay, I think we did not discuss how to convert dynamic programming to function approximation case. Like so, for example, it's really simple. Like for example, like if I want to do semi-gradient DP, the update will look something like this. So WK plus 1 is equal to WK plus alpha times for all the states, summation over all the states, expected value of RT plus 1 plus gamma of VST plus 1 given WK given ST is equal to S minus V of S given WK and the gradient of V of S given WK. Okay, so what I'm doing in semi-gradient DP is I consider all the states, I take the expected update, the DP update for all the states, and I compute gradient for that. Okay, now there is no asynchronous nature here, right? Like so, because I'm considering all the states for the updates. If If I have 100 states, I'm considering all the 100 states. Also, there is no stochasticity here because these are expected updates, not sample updates, right? Even with such a semi-gradient DP update, you can see in the right-hand side that they all diverge. Okay, now this is a problem because what we have here is really a simplest possible combination of bootstrapping and function approximation, right? So semi-gradient DP is the simplest possible bootstrapping you can think of. There is no asynchronous nature, there is no stochasticity, right? So it's a complete like synchronous algorithm. Such a simple bootstrapping approach, it's not as stochastic as TD, right? So it's a very simple bootstrapping approach, which is combined with such a simple linear function approximator, okay? But we cannot learn a good value for the W's here, right? So this is not possible because we are an off policy estimate, like off policy distribution, okay? Now, suppose we change, okay, so are there anything else that we need to consider? Like we need to figure out where the problem is, right? So so the problem that we are facing here is, probably I will write down the problem. So the problem that we are facing here is we have three things: function approximator, bootstrapping, and off policy trading, right? Now, when I combine all these three, I get instability. What could be the reasons for this? Like, so we have already crossed out some of the reasons. Like, so is it because of stochasticity in the bootstrapping? No, because DP is not stochastic, but still we diverge. Is it because of the asynchronous updates? Right? It's also no, because we are not doing asynchronous update in DP updates, right? Like, so there is another one more reason like we could think of, which is it because of this one-step thing that we are doing, right? So now we do this one-step return, right? Is it because of the one-step return? Like, so now to test that, what if instead of doing one-step returns, we do the least squares approximation, like, which is basically the idea of instead of doing like incremental updates, I directly find the approximate solution, right? So if I can do that least square solution for every iteration, okay, so then probably we will not have the stability issue, right? So it so happens that it is also not the reason for this, okay? So we can prove that with a very simple example. So this time, the example 3 is given by Sid Siklis and Ben Van Roy. This is one of the famous examples that people often use to show that off-policy learning diverge, okay? So now this example is just an extension of the first example, okay? So you have this W to 2W. But from 2W state, we are going to have like an action going out, okay? So with 1 minus epsilon probability, you stay in the same state. With epsilon probability, you go to another state, like you terminate, okay? The rewards are still 0, all the places, okay? Now, let us try to do least square solution here, like, which means no more gradient update, like we are taking one-shot solution, okay? So now WK plus 1 is going to be argmin of W belonging to W. I'm going to construct the least square loss. So the loss is going to be summation over all possible states, value of the state minus expectation with respect to pi RT plus 1 plus gamma times V of ST plus 1, given WK, given ST is equal to S, the whole square, right? So this is just the least square loss for LSTD that we have seen before, right? So now there are only 2 states. I can expand this loss. So this is R min W belonging to R. For the first state, the value is W. And the update is minus gamma times 2WK, right? Whole square plus. For the second state, the value is 2w minus, with 1 minus epsilon probability, you say stay on the same state. So it's going to be 1 minus epsilon times gamma times 2wk, the whole square. Okay. Now, this is a simple function. You can differentiate this with respect to w, set it to 0. Okay. I'm not going to do that now. A very simple exercise. So you differentiate this, set it to 0, so you're going to get the solution. The solution in this case is 6 minus 4 epsilon by 5 gamma wk. Okay. Now you can see that this sequence of wk updates is going to diverge whenever gamma is greater than 5 by 6 minus 4 epsilon, and w0 is not equal to 0. Is that clear? So this is puzzling, right? Like, so, like, even if I do complete least square instead of one step return, I will still diverge. Is that clear? So now why is this happening? Like, we're going to discuss a little bit more detail, like after the break. Is there a question?
Yeah, it's the third time repeating the same question. Where is the off policy role in that again? Because like it still seems like it's the issue with gamma, and now you have you are considering the entire MDP now, like all the states and all the updates and everything.
Yeah. Well, so the role of off policy in all these places is, like, for all these.
Like I see the role of function approximator because you are doing this, you are representing it with W and everything. Bootstrapping, you in this case I don't see it. Off policy again I don't see it.
Okay, so
Like,
now,
it's more like it seems like an issue with problem design now that
okay,
gamma
maybe
is,
I missed something. Okay, so in the second example, right, like if I go back to the second example, the policy that we are estimating is pi, which is basically always taking solid action. Okay, so the target policy is different from the behavior policy, and like in almost all these examples, right? So if you do on policy learning, you can actually show that you can converge. So we will talk about this after the break. So we'll take a 10-minute break.